Hi everyone, welcome to another lecture in our data science course, and today we want to talk about tree-based models and more specifically about random forest. So today we want to talk about what a tree is in a mathematical sense, and then you might guess that you can build multiple trees to get a forest. And yeah, this is what we want to do. So let's look at the first example of a tree, more specifically a classification tree. So here you see an artificial tree I generated on some fictitious data set that contains the number of Taylor Swift songs someone listened to in the last 100 songs. So how many times did Taylor Swift appear in the last 100 songs that you listened to, and also the data set contains information on how many numbers of Taylor Swift concert one attended. And just from that we can find a model as depicted here that uses some simple decision rules to decide whether someone is a Taylor Swift fan, so a regular Taylor Swift fan, not a Taylor Swift fan at all, or a really true Swiftie, so a huge fan. And yeah, this here is really a simple decision tree, and we want to figure out how we can actually automate the process of finding such a tree. And these tools, like these tree-based models, are really versatile. They can also be used not only for classification, as is done here in this example, but they can also be used for regression. So for instance, these final nodes here, so the tree nodes in red, they don't have to be labels as in categories, they could also be constants, so just numbers. So in this case, this tree, if this would be a regression tree, would be able to predict 3 different types of numbers. So number 1, number 2, and number 3. And let's see how that is done. So for instance, take a look at the Palmer penguins data set, which contains measurements of penguins. For instance, here you can see their bill length in millimeters. Here's their flipper length in millimeters. And the color range depicts their weight. And here we want to fit a regression tree that gives us back the weight. So here we want to find a model that gives us back the weights, which is obviously not a categorical variable but a numerical one. And here it might be a little bit harder to imagine how a tree is supposed to look, but in the end it's all the same. It's the same procedure as with the classification tree. The point is to split your space of predictors, so in this case this 2D plane, into regions, and in each region all the points are assigned to one and the same label, or in the regression tree to one and the same value. So what a regression tree does is it splits this up into simple regions, and then it assigns a value to each region. So in this case it would look something like that. And as you can see here, it split the whole plane of predictors that is spanned by the predictors. Of course it works in higher dimensional space as well, but it's not as easily plotted. So this is why we look at things in 2D here. So we have 2 predictors. And yeah, you see here this plane is split into 5 areas, and in each area there's one corresponding constant that is fit to all or predicted for all observations that fall within a region. So say here you can see the shading is like light green. Then you could look up what is light green, I don't know, something between 5,000 and 6,000. So all the values or all the observations that fall within this region would be assigned that value. And this way you could use a tree for regression, and for classification you wouldn't assign a number, a constant, but a label for a tree. And that's basically it. And yeah, so in this lecture we'll have to find out how we can find these regions, how we can do the splitting of the predictor space to assign different values. So first we will talk about regression trees, and then we'll see how we can make that use the same ideas to get a classification tree. So in the end, a regression tree can be put into a simple formula. It's a prediction of a response variable, as always, that is that uses predictors x1 to xn, and in the end it just checks whether the vector of the predictors falls into a specific region, and then it assigns a constant. So in the end, the fitting procedure of the decision tree is about finding those constants here and the number of regions, and so the regions and the number of regions. Of course, it's not determined from the beginning that we have, say, 5 regions or so. This will also depend on the data. And what we do is we use simple splitting rules that split a region into 2 parts. So we have a predictor variable xj, and then we'll use some value s that splits the space into 2. So for instance, in the previous example, we could start out with just the whole plane, and now in the first step we split it into 2, and then we figure out take one of those areas and split that into 2 again, and then we can iteratively redo that again over and over again until we reach some conclusion when we stop to split. That's the idea. And of course we will need to figure out how do we actually find these. So how do we find out what of our predictors we use for the splitting? In each splitting step we only use one variable, and what is the value we use to split. And this will, in the regression case, will depend on the constant we would assign to the 2 new regions. Right, so first we have one region, so only one region, and we split that into 2. And therefore we need, for these 2 new regions, we need 2 new constants that would be assigned to all observations that are in this region. And depending on those chosen values, my regression quality, so my performance, would be either good or bad, and the point of it becomes to find suitable constants that would minimize the error, the prediction error we get, given that we've already split into 2 regions. So given that we've split into 2 regions, we'll need to find the constants. So in each region we can minimize an impurity measure. Basically it checks what is the error in a specific region. If I assign a constant c, then all the observations that are within that region, so these are the predictors, and the corresponding response variable is denoted by y. What is the basically the mean squared error within that region? But the point of using this impurity measure is that we know what constant c would minimize this error in a region. It is simply the average of all the response variables in that region. So we don't actually need to find the constant c, because that we can immediately conclude from our splitting, because then we know what are the observations in the new regions, and then for each region we simply compute the average, and we know this will already minimize this impurity measure. So our minimization problem of having to trying to find the best splitting point, splitting variable, and constants that are assigned to each region reduces actually to only finding the splitting variable and the constant that we use for the value that we use for splitting. And this is actually easy to compute by just going through all the possibilities. And so in the end it's just more or less trial and error. We try to minimize this impurity measure. So we split according by a variable j and point s if this part here, so the impurity measures for the 2 new regions with respect to the average, the constant that is given by the average. So the sum of that will be the new error we have from our splitting, and we try to get the error of course as low as possible. So this is how we can iterate through, in each splitting step, iterate through all possibilities more or less to find the splitting variable and the splitting point. And once we have done that, we have split the region we looked at into 2, and then we can start over again. We can take a new region and then split again, and so on. And we simply do that until all regions are basically small enough. So you could say stop at if in a given region there are only 5 observations. So 5 is my minimum threshold. I always want to get at least 5 observations in a region. Then I wouldn't split a region further if it is already at these 5 points. That's basically it. And of course you could still try to split other regions that still have many observations, but you won't split the region that is already at this minimal threshold. And yeah, that's basically the splitting procedure. We still need to cover how we then actually choose the final tree, because right now we have split the reach or the prediction space as finely as possible. So we have a lot of splits, but this might actually lead to overfitting. So we need to decide maybe it's better to have a few less splits. But we'll come to that in a second. First, let us talk about how we can go from a regression tree to a classification tree. Because right now, our impurity measure is what stops us to apply the same procedure to classification problems. Because if you look at the impurity measure, then you will see that of course the response variables in the classification problem are categorical labels, and it doesn't make sense to compare it to just some arbitrary constant, and also you cannot really average the labels in a given region. So we will need to find a different impurity measure, but once we have that, the idea is still the same. Simply split the areas according to what minimizes the 2 new regions, or the error of the 2 new regions. So what is a suitable impurity measure for classification? This would be, one possibility would be the Gini impurity measure. There are others, but one really popular one is the Gini impurity measure, which looks like this, where K denotes the levels of categorical categorical response variables. So in our Taylor-Swift example, we had 3 levels. We had no fan, not a fan, regular fan, and true Swiftie. These were our 3 levels. So in our case, K would be 3. And then P hat of R and K denotes, for a given region, denotes the proportion of observations of a given level. So for instance, P hat R1 would give the proportion of observations that have label 1 in region R. That's basically it. And this Gini impurity measure might at first look weird, because it's not really a comparison as before. Before we had like a comparison, this is my true value, this is what I fit to the value, compare the two by difference and then square it. It might first be weird to not find that in the Gini impurity measure, but the point is this part here, or this whole part here, can be interpreted as that this measure quantifies for a specific region R how often a randomly chosen observation would be labeled incorrectly if you would just randomly assign a class label according to the distribution of the labels within R. So if you have P hat R1, R2 and R3 in our case with the 3 different levels, then you would have values that sum up to 1, so it is a distribution, and you could then randomly assign a label to each observation in the region according to that distribution, and this Gini impurity measures how often would you be wrong, basically, or how often would a randomly chosen element from that region would be labeled incorrectly if we would label according to this random distribution. So it's, in a sense, it's an indirect look at how do we find or how how bad is our classification or how good is our classification given this random assignment. Okay, so it's a different impurity measure, but then everything else stays the same, and we can simply split as far as we want until we reach this minimum threshold, and then at the end there comes the point when to decide, okay, what will be my final model, what will be my final tree. Because if you, as I said, split the predicting regions too far, then you are resembling the data too closely again, and then you're coming into the danger of overfitting. And the idea then is to not use the final tree with all the possible splits, but use one of the trees that you got in between. So you will actually need to save all your intermediate steps of splitting, and therefore for each new configuration of splits you will get a new corresponding tree. And the point now is basically to find out from the five just say 5 trees that you have until you stopped splitting. How do you choose the one that's more or less perfect or has some form of doesn't overfit too much? And this is done with the so-called cost complexity criterion. And so we choose a tree so T will be a tree. Absolute value of T is the size of the region, or the number of regions that you have in a tree, or corresponding to the tree picture, the final nodes of that tree. And so we would simply sum up for each region that we have, sum up the impurity measure, so this would be my total error. And we know that this part here, the sum, of course, is minimized for the final tree, so the one that has all the splits in it, because that was the point of splitting, to minimize the error, to make it as small as possible. So for if we would only look at this as a criterion to choose the final tree, we would always choose the last tree. So this is why there is a second term in here, which actually considers the tree size and penalizes that. So alpha is a constant that is greater or equal to 0. So for alpha being equal to 0, the tree that minimizes this whole criterion is the final tree. And depending on what alpha I use, some other tree along the chain of trees I constructed earlier would be the tree that minimizes the cost complexity. And so to find the final tree, we actually only have to find a final value of alpha. So what alpha value do we want to choose? And once we have chosen one, we can check, okay, I have now 5 trees, say, and for these 5 trees and this given alpha, which tree has the lowest cost complexity criterion, and that could maybe be the second or the third tree, and then I would simply choose that as my final tree. That's the idea of it. So we have reduced our problem of finding a tree to a problem of finding an alpha. And the problem of finding alpha is a bit trickier, so I don't want to go into the details of that. Let's just say it uses cross-validation in some form to find the alpha. And if you wish to find out more about how to find this alpha, simply take a look at the lecture notes, and there you will find a reference to YouTube where I find a nice video that explains this last step of the cross-validation in more detail. For our purposes, though, it's a little bit out of scope, so I just decided to leave it out. I think the idea of how a tree is split is should still be clear now. Okay, so in the end we have found this final value of alpha, so that means we have a final decision tree. It now becomes time to figure out, okay, we have one tree, how do I go to a forest full of trees? That's the idea of a forest, use multiple trees. And in general, that's the idea of ensemble learning, meaning that you use multiple you fit multiple models and then combine all of the predictions from each model into one final prediction. That's the idea of ensemble learning. And more specifically, if you use bootstrap samples, for instance, then it's also referred to as bagging. So in the end, building a random forest is nothing else than generating bootstrap samples from our original data, and then with this data, with these bootstrap samples, for each bootstrap sample, generate a new classification or regression tree. And then if you want to predict a given observation, you can predict it according to all of those trees that you fitted early on. And if you then want to combine it into one final prediction, you either average all the results you get at the end, if it is a regression, if you are looking at a regression problem, or if it's the classification problem, you simply decide by majority. So what did most trees decide on? So maybe most of the trees decided for label 2, whatever label 2 is, and then your final prediction would actually be the label 2. So that's actually a pretty simple idea, and it works remarkably well. One thing, so what I've described now is this ensemble learning idea, and more specifically bagging. That's what it's called, using the bootstrap samples to aggregate predictions. But one thing random forests do on top of that is that they not only use bootstrap samples to fit the tree, they also use decorrelated trees. So they try to decorrelate the trees as much as possible, and they do that by, at each splitting step, make sure that not all the data is used. So not in each splitting step you cannot use all the variable. So before I split, I simply randomly choose a handful or whatever, how many splitting variables as potential splitting variables. And once I have done that, I can just do my regular splitting procedure, and then in the next splitting step, I choose potential splitting variables from all predictors again, and then this way I build the new trees. So this will give more, let's just say, more variation to the trees, and that actually decorrelates them, so that the correlation between those trees is not as high as if you would always in each splitting step potentially look at all variables, all predictors to split. And this is why the random forest works even better than if you would just look at bootstrap samples and do the tree fitting just in the regular way. So that's the idea of random forest. Let's check how we can do that with the tidymodels framework. So let's look at Titanic Forest. In the previous chapter we fit a logistic regression for our Titanic dataset. Now we want to fit a random forest. And the idea is pretty simple. All we have to do is change most of what we have to change is simply change the model specification. So going from logistic regression, we go to rand forest as a random forest. And then we see here, we actually have hyperparameters, it's what it's called. So parameters that are tuned. So here I can decide how many trees should my ensemble have, or how many trees should my forest have. And then I have some variables m try and min n. And these refer to as this one here as the minimum number of points in a given region. So this is the minimum threshold I don't want to cross. And the m try is the random number of predictors I sample at each split. And of course, here it is not really clear how what is a good choice for that. And in general, there is not a rule of thumb or whatever to choose that. So this is why you actually need to figure this out from the data. And so this is why it needs to be tuned. This is what we call it. This is why here we have a function tune. Whereas here with the trees, we simply say, okay, just make sure there are enough trees, just use 1,000 trees. We simply put a number there. But here we say, okay, hold on, the model is not final yet. We will need to tune these parameters. This is basically what we're saying. And then the mode is classification in our Titanic problem, but note here forests could be used for regression as well. And the engine is Ranger, which is just a popular implementation in R, so don't worry about that, just simply always use Ranger. That's more or less it. I didn't mention it here in the slides, but now that I think about it, probably I should have. Of course, we will need to also change the recipe a bit, because in the recipe we had in the end a few steps that were specific to logistic regression, so making sure that all categorical variables are transformed to factors, or I don't know, all the numerical predictors were standardized so that they have mean 0 and standard deviation 1. And some of these steps, or actually a lot of these steps, we don't need for random forest because they are actually easy to maintain. They're really easy models. You just take the model and take the data and throw it at the forest. The forest will hopefully figure out what's going on there. But the idea is you don't need to do a lot of pre-processing for those. I think that's probably also a reason why they are so popular. But so what I'm trying to get at is that my statement that you only need to change the model specification as we've done here is not completely correct. You will need to also change some of the technical step you added to the logistic regression because the random forest doesn't need them. Okay, that's the idea. So let's talk about how to tune these parameters. How do we find an optimal choice? The idea is simple. Again, we simply iterate through a lot of choices. So here I simply generated a grid. So I'm saying potential candidates for min n are 5 to 7 and the potential candidates for m try are 1 to 4. These were just random numbers. In the end, it's educated guessing, I would say, that you use when you try to figure out what are potential candidates, but in this way you can find a grid. And then you can use grid tuning to simply iterate or fit the random forests given these parameters. So you will fit it once with these two parameters, then with these, and so on. So it's a really a simple procedure, and then you will check the performance of each model that you fitted according to test data, and then you simply decide which model of those performed best according to the test data and some metric you want to optimize. So say this pair of parameters minimizes the area under the curve, then you might want to take these as your final parameters. And yeah, that's basically it. As I said, it's a very simple procedure. There are more intelligent procedures that try to do it more intelligently, so not doing trial and error, but just using some start point, and then the algorithm is supposed to figure out where to go next. So maybe it's something like a gradient descent. I'm not 100% sure, but in any case, there are more intelligent procedures, but here we'll simply do grid tuning. And in tidymodels, it's actually easy. We simply have to use the tune grid function to do the grid tuning for us. All that it needs is the workflow we have from last chapter. It will need the resamples for the training and testing to actually check what is to evaluate the performance with the testing data. This is why it will also need the metrics you want to look at, so you can actually look at multiple metrics simultaneously and later on then evaluate one or more metrics. And then you will, of course, for the grid tuning, need the grid that we've just defined. And as before, there is a control argument. So we have seen that in the last chapter that these tidymodels functions also have these control arguments. And here there's a function control grid, which allows you to control the grid tuning. And in this case, I used it to save the predictions and to make sure that the tidyverse package is always attached to each worker of my parallel processing, because random forest can be quite computationally expensive. This is why it helps to do parallel processing if your computer has more than one core. So in here I used 6 cores, or 6 threads more appropriately, to do some parallel processing, and this is why I needed this. Parallel processing in itself is a quite extensive topic, so we won't deal with that at all. Just know that here I've simply given you this one line of code, which then in turn will need this additional part here too, just to give you a quick and dirty way to speed up your computations. So yeah, this is the tuning procedure, and once you have done that, you will get results again in a sort of convoluted way. Everything is stored in a tibble with list-like columns, and this is again we have functions that pick out the information from that tibble that we want. In this case, we can simply say, okay, show me the best parameters that minimized the following metric, and then you simply state the metric you want. Of course, this needs to be one of the metrics you specified earlier. So here we have the area under the curve specified. So this is why we can consider it here. So yeah, here you see that these two parameters actually minimize the area under the curve, so we might want to go with those. Actually, if I look at the number, the mean here is lower, but also the standard deviation is higher. So I guess there is some rule implemented in the show best function that actually considers both the mean and the standard error, but I'm not entirely too sure. But in any case, most of the cases you can simply go with whatever is depicted as best here, and you can simply select that best value with select best, and then recall that you in your workflow, or more appropriately in your model specification, you had these tune functions instead of just numeric values as with the trees argument. You still need to get rid of that before you can do a last fit. So this is why you need to finalize your workflow with the optimal parameters, and then you can do a final fit. And here you see that we didn't run into that much overfitting, because it's very similar to what we already had here. Okay, yeah, so that was our lecture. It has kind of been a busy week for me this week, so this is why there is no dinosaur this week, but I promise there will be something next week again. So yeah, that was our lecture, and see you next week. Bye.